Mechanism of keto-enol tautomerization. So how do you initiate the reaction? In order for the reaction to take place, you need to have an enol or an enolate. So enolate is the negatively charged carbonyl, alpha carbon. So there are two ways, as you've seen before. There's a base catalyzed and there's acid catalyzed. So let's begin with the base catalyzed. With the base catalyzed, let's draw this. You have, of course, let's say we have an acetone here. You have a base, let's say such as hydroxide. So again, this is resonance stabilized. This is probably now the fourth time I'm drawing this, so you should be able to draw it very easily. So you have a CH2 here. Now, of course, you can protonate this. Let's say we have water here. This is negatively charged. So we have water, we can protonate. So this is the keto form, and this is the enol form. Now, we say that for simple ketones, the keto form is more stable, as we explained before, than the enol form. Nevertheless, the enol is a crucial intermediate in a variety of reactions with ketones and aldehydes. So the reason why we need reactions that undergo, that you have the starting material, or at least one of the materials as an enol, is because you can form a carbon-carbon bond versus, having it attacking, if you have the ketone, then you will not be able to undergo these reactions that form the carbon-carbon bonds. You may, again, attack the carbonyl, and we've seen those reactions in the last 3 chapters. So now the enolate ion is a powerful nucleophile, and that's why there's an emphasis on enolates. So if we have, of course, an enolate formed, now this can be written multiple ways. You can leave it like that. I generally sometimes like to leave it like that, or you can, of course, draw the resonance structure of that, which is either one is acceptable, so there's no need to ask me which one to use. Once again, I like to see the negative charge as a nucleophile. So once again, you have an electrophile here. You have an electrophile. Attack. Attacks. Notice how the double bond here. Attacked versus the lone pair here. And of course, what are you forming? You are adding now an electrophile, whatever that is, right there. So you're attaching something. So it's like it could be another carbon that you are attaching. Now, what about having an acid catalyzed reaction? So before we go, again, this is the alpha position. So here again, we say we added an electrophile to the alpha carbon. So this is important, or the alpha position. So what about having an acid catalyzed? You probably already know that in an acid catalyzed, we've seen that the carbonyl carbon gets protonated first. So we need to draw out the H's. So if we have an acid catalyzed, we're going to use an acid, and that's involving the hydronium ion. So we have there it is. So remember, protonating the carbonyl oxygen makes the carbon more electrophilic here, but there's no attack, so you can't attack it because you have water. But what's going to happen now is the water, obviously, is going to act as a base and deprotonates one of the H's. So actually, we're actually going to just do it in one step. Actually, the direction is this way because it's acidic. Is that all actually going to go like this? So you're going to have a double bond here and an OH. So you formed your enol. Right there. So all in one step. I didn't want to draw the steps in between, so that would be actually the mechanism for it. So an enol has an electron-rich double bond. There it is, right there. That's the electron-rich double bond. When electrons from this double bond attack an electrophile, the resulting cation is stabilized through resonance with the oxygen atom. So once again, we're going to repeat doing this because it's important. Is if you have, so let's actually redraw it this way so it makes sense here. And let's say we have an electrophile. All of these are, again, the general mechanisms. We're going to see them more specific as we learn about the reagents we're going to use. So you should know that these electrons come down as well. And you would produce, okay, electrophile right there. So we added the electrophile right there. Now, of course, so we have the double bond right here with a positive.